Okay, let's find the distance from LA to Tokyo, and in the process, do some work with spherical coordinates. We'll derive the formula that takes spherical coordinates to Cartesian or rectangular coordinates. We'll derive the formulas that do that conversion. We'll look at how latitude and longitude relate to spherical coordinates, and then with all that, we'll put it together along with dot products and vectors, and we'll use that to find the distance from one point to another on the surface of the Earth. Okay, what we're looking at here on the left side is a visualization to understand how spherical coordinates work. So you can imagine now any point in three-dimensional space can be described with x, y, and z, and those are rectangular or Cartesian coordinates. That's what we're most familiar with. But we'll begin to become more familiar with spherical coordinates. We can use this a lot later in the course. So imagine any point in three-dimensional space, call it point P. Now to identify that point with three values in spherical coordinates, you could begin with rho. This is rho, and that's a distance that's we can say for spherical coordinates we can take rho to be always positive. We can identify the point as how far it is from the origin, and then we can measure this angle theta to this line that contains the point P. This angle theta, positive thetas are counterclockwise from the positive x-axis, just like they are when we study polar coordinates in two-dimensional space. So positive angles are counterclockwise from the x-axis, and negative angles actually go clockwise from the positive x-axis. And so theta could be positive or negative, go from from 0 to 360 or past 360 or negative. So that's theta, and then there's also this. So this is theta, and then there's phi, and phi is an angle that in spherical coordinates we will measure from the positive z-axis down to that point in three-dimensional space, or down to the. It's basically the angle between the positive z-axis and the vector that points to the point P. So that angle phi will always be between 0 and 180 degrees, or 0 and pi. Alright, so with those three numbers that we can locate this point in three-dimensional space using spherical coordinates. In cylindrical coordinates, we have some angle theta that we measure just like we did before from the positive x-axis. We have some distance r that in cylindrical coordinates we can just keep that r value positive. We can have positive or negative thetas, a positive r, and then some height z up into the three-dimensional space, and that's how we identify that random point in three-dimensional space in cylindrical coordinates. Let's take a look at this a little bit more carefully one more time. So identifying that point in three-dimensional space, I have rho, the distance from the origin. I have theta, this positive theta angle. If it's positive, it is counterclockwise from the positive x-axis, and theta could be negative and goes clockwise then from the positive x-axis. So it's a angular rotation in the xy plane. And then I have this angle phi that measures it is the angle between these two vectors, right? Between this positive z and the vector that locates the point P. So that's phi. And that angle in spherical coordinates is always between 0 and 180. Cylindrical coordinates, I have some distance r that I can just keep positive all the time for any point in three-dimensional space. Here's the point that we're identifying. So r is this length in the xy plane out to this point directly below P. Theta is a angle in the xy plane, and then z is the height of the point in the on the z scale. So of course z could be negative and it could be below the xy plane. If in that case it would be like having an angle that was more than 90 degrees for this angle phi. Okay, here we will derive conversion formulas that will allow us to convert spherical coordinates into rectangular coordinates. And to do the conversion, we'll also need to use cylindrical coordinates, and therefore we'll also even need to use polar coordinates. So I always like to think of this as like, why do we need polar coordinates? Well, one reason is then we can do cylindrical coordinates. And if we have cylindrical coordinates, then we can do spherical coordinates. So we need polar coordinates to be able to understand spherical coordinates. We could use those spherical coordinates to do all sorts of things later in Calc 3, but right here what we'll do is use them to figure out the distance between 2 points on the surface of the Earth. So you'll see that my derivation kind of goes through this process. Imagine we were given rho and theta and phi. We'll then convert that into r, theta, and z, which represent the cylindrical coordinates. And then from that, we'll convert it into the rectangular coordinates. So if we're given rho, theta, and phi, the cylindrical coordinates would be r, theta, and z. And how do we calculate each of those? Well, maybe let's start with the r. How do we find the distance here to this point? So let's call this point P, and we'll call that point Q. Q is a point that is in the xy plane, that is, you could say, directly below or above the point P. The point Q would just have the points, the coordinates x, y in two-dimensional space. And then the point P has the same x and y, and it just has a z value. So I'm trying to figure out, where does this come from? How do we get r equal to rho sine phi? Well, rho and phi are given values that I can compute r, and maybe you can see it if I move this dotted line up here. The reason I'm doing that is because I can also imagine a 90-degree angle here. And so then I have this triangle in three-dimensional space that this is r here. And here's phi. And if I did the sine of phi, I can say the sine of phi is the opposite over the hypotenuse. And the opposite is that length r, and the hypotenuse is rho. So that's how I get r is rho sine phi. And in the same way, we could figure out what z would be if we knew the rho and the phi, because we could say that z value is the position on the z-scale. So let's just take this and move it over here and say, how do we find that height z, or that value z here? If this is z, well then again I have a triangle, a right triangle, and to find z, I could say that the cosine of phi is the adjacent over the hypotenuse. And that's where I get z is rho cosine phi. So having this point in spherical coordinates, I can convert it into what the r would be in cylindrical coordinates and what the z would be in cylindrical coordinates, and the theta in the cylindrical coordinates is the same as the theta in spherical coordinates. Okay, so let's just pause on that for a second and say, all right, if we had spherical coordinates, rho and phi and theta, we could compute the cylindrical coordinates. We would use these formulas. Now let's take a real quick review of polar coordinates. Remember that point Q that's in the xy plane? It had coordinates x and y in rectangular form, and it has polar coordinates r and theta. Well, I could figure out what the x and the y are knowing the r and the theta, right? Because I know the cosine of theta is x over r. And so I solve for x and get x is r cos theta. And if I knew that point Q in the xy plane, if I had the r and the theta, then I could find the y value, because I know the sine of theta is y over r, the opposite over hypotenuse in a right triangle. But that's generally true for any angle theta. That's really ultimately how sine is defined. It's this y coordinate over this r value, where r is held positive. So now I'll say that if I had phi and rho and theta, I could compute my cylindrical coordinates. And if I had those cylindrical coordinates, I could compute my rectangular coordinates. So we've got all the pieces finally together. Let's say, so now we've got all the pieces. We can say, since x is r cos theta, and r can be found with the spherical coordinates, we could say x is rho sine phi times cos theta. Because this is r. Right? And then I could find the y coordinate in rectangular coordinates by using the cylindrical coordinates, but the cylindrical coordinates, I can get those from the spherical, right? Because I know r is this rho sine phi. So there it is again. Rho sine phi times the sine of theta. And then the z I can compute from the cylindrical coordinates, from the spherical coordinates, they're in cylindrical coordinates. That's rho cos phi. Knowing the spherical coordinates, I can compute what the cylindrical coordinates are for z, but that value in cylindrical coordinates is the same z value in the rectangular coordinates. So that's it. We've reached some kind of conclusion here. Given a point rho, theta, phi in spherical coordinates, we could calculate x, y, z in rectangular coordinates with these formulas. All right, so now just a quick review that latitude measures angles from the equator. Imagine a point at the center of the Earth measuring up for positive angles up to the North Pole directly above at 90 degrees, and negative angles from the center of the Earth measuring down to negative 90 degrees at the South Pole. And these lines of longitude go around the Earth east and west, and we'll take 0 degrees longitude to be right through England, called the prime meridian, and we'll take positive angles. So this is again measuring angles from the center of the Earth around, but we go for positive angles to the west from 0 all the way out to 180 degrees on the opposite side of the Earth. And then negative angles of longitude can be west. We'll consider to be west. And each of these is actually 15 degrees. So there's negative 30 and negative 45 and negative 60. And these now are negative angles that measure the direction to the west from 0 to minus 180 all the way around the world. So the longitude measures the east and the west, and the latitude measures the north and the south. So now we can see that latitude and longitude are convertible into spherical coordinates. Let's just start with, suppose this was the Earth and the equator was right there, circle in the xy plane. This point P could be some point on the surface of the Earth. And so theta measures our longitude, phi is the co-latitude, and rho is the radius of the Earth, right? We'll assume a constant radius on a spherical Earth of rho equal 3960 miles, 3,960 miles, or 6,373 kilometers. And so phi in spherical coordinates is really a co-latitude. That is, it's the complementary angle. Phi is the latitude subtracted from 90 degrees. For example, if latitude was 40 degrees, and you could see it to the equator, the angle measured to the equator in this right here, if this was 40 degrees latitude, then phi would be 50 degrees. The co-latitude, the complementary angle, it's the angle to the North Pole from that vector that points to P. And this is the longitude. Theta is the longitude. Theta measures longitude from the prime meridian at 0 degrees. We could say that the prime meridian would then fall right along the x-axis. And at measuring, so at theta equals 0, you're right on the x-axis, and that goes through Greenwich, England. And negative angles are going to be west of England, and positive angles are going to be east of England. Now let's go a little further, looking at how would we calculate the distance between two arbitrary points on the surface of the Earth. Let's find this distance d that I've labeled in the figure here. the distance d between points A and B, any two arbitrary points on the surface of the Earth. Well, the way that I'll do it here is to find two vectors that point from the center of the Earth to each of those points on the surface of the Earth, and then I'll find the angle between those two vectors, and that's it. Once I've got the angle between those two vectors, I can quickly calculate that distance in that arc between those 2 points on the surface, and I'm going to use this formula to do it. And to explain where that formula comes from, it goes back to really the very beginning of trig, when you learn what a radian is. You might remember seeing it written in this way, where this arc length s is related to the radius of a circle, and this angle that's subtended by that arc, it's related according to this equation. It's this equation that also really defines what radians are. Radians are the angles that you get when you take the length s divided by some length r for the radius of a circle. You get the angle in radians. And so I can use it in this way, that if I multiplied the length r, the radius r of a circle, times the subtended angle theta, I get this arc s that goes along the circle. And that's really what's happening in this picture too, but in three-dimensional space, where I can imagine a plane that contains the two vectors a and b, and in that plane there is a circle. Right, there's 3 points that make the plane, the origin and the center of the Earth, and then these 2 points all form 3 points that form a plane, and in that plane there is a circle that has a radius rho. Rho is the radius of the circle, alpha is this subtended angle, and d is this arc along the circle that would correspond to that angle alpha. So that's how we'll calculate the distance between the 2 points. Fundamentally just multiplying the radius of the Earth times the subtended angle, but that angle must be in radians. So let's begin with taking 2 points on the surface of the Earth given in terms of their latitude and longitude. So Los Angeles is at 33.9 degrees north and 118.4 degrees west, and Tokyo is at 35.5 degrees north and 139.8 degrees east. And of course I'm using assumption of a spherical Earth with a radius rho equal 3960 miles, so I'm doing this calculation in miles. So in spherical coordinates, what I would do is start with the rho at 3960, and then I find the longitude, but because it was west, longitude I'm going to use in my spherical coordinates to distinguish between west and east. I'll use pluses and minuses, and so everything to the west I'll make negative, so it has to be negative 118.4 for the angle, and actually this is actually degrees. And then the co-latitude is based on actually knowing the latitude for Los Angeles, and the latitude for Los Angeles was 33.9. So if I take 90 minus the 33.9, I get 56.1 as the phi, and this was theta. And those are the spherical coordinates for Los Angeles in three-dimensional space. Now if I want to get the spherical coordinates for Tokyo, I'm going to use the same radius of the Earth, that's rho. I'm going to just use exactly 139.8 degrees for theta, because it was east, and so it's positive. But then for the angle phi, I need to get the co-latitude, and so I'll read off the latitude for Tokyo at 35.5 and subtract it from 90. Yep, and that's the 54.5 degrees that I'm using in spherical coordinates for the angle phi. So now I have both points in three-dimensional space in spherical coordinates because I got that from latitude and longitude. Knowing their position in latitude and longitude, I can convert that into spherical coordinates. And if I have the spherical coordinates, I can compute their positions in three-dimensional space in rectangular coordinates. Once I have those rectangular coordinates, I can form those vectors, then I can find the angle between those vectors, and finally compute the distance along the arc on the surface of the Earth between those two cities. So the next thing I'm doing here is using my rectangular coordinate conversion formulas, and I'm just plugging in those values that I had for LA and Tokyo. So of course the radius of the Earth, rho, is 3960. The angle phi, that was the colatitude, that was 56.1. And theta, that was the longitude, but because it was west, it's negative 118.4. Type all that in the calculator and you come up with negative 1563.3. That's the position on the x-axis in miles in three-dimensional space for that point on the surface of the Earth. And then I'll do the same thing with the y-coordinate, rho, 3960. Phi is the same angle. Theta, it's the same as it was there. I get negative 2891.27 for the y value. And rho cos phi, 3960 times the cosine of the 56.1. That gives me 2208 on the z-scale. All of these units are in miles. So that gives me the rectangular coordinates for the point. And then, of course, I can write a vector that goes from the origin to that point. So you see that I'm using brackets to indicate the actual vector that goes from the center of the Earth to the point at which the city of Los Angeles is located on the surface of the Earth. And I'll do the same thing with Tokyo. For Tokyo, I had spherical coordinates that I can plug in to my conversion formulas. Radius 3960, longitude 139.8, colatitude 54.5. Plugging those into my conversion formulas, I get the x, y, z values for the position in three-dimensional space in rectangular coordinates for Tokyo. And those three x, y, and z values in rectangular coordinates I can then just copy into the components of a three-dimensional vector that points from the center of the Earth to that particular point. So now I have these two vectors that locate those points on the surface of the Earth, and I want to find the distance between those two on the surface of the Earth, which really just means finding that arc of the circle that's at that radius, the endpoints of those two vectors. Right, so I'm back to this question now of figuring out the distance from LA to Tokyo on the surface of the Earth. That distance d is what we're trying to figure out. So we can copy our vectors that we had just calculated. And how do we figure out this angle alpha? It's the angle between two vectors. And we have a way to do that. It's the dot product. It's the dot product that gives me an angle between two vectors. Really, I'm just using the dot product of the vector tk for Tokyo with the vector LA for Los Angeles would be the magnitude of the vector tk times the magnitude of the vector LA times the cosine of the angle between them. So we'll be able to solve for the angle because we could do the cosine of alpha is this dot product divided by these magnitudes. So solving for cosine alpha, it would be equal to this dot product divided by these magnitudes. And from there, I'll be able to solve for alpha. Alpha would be the cosine inverse of that dot product divided by those magnitudes. Alright, so to find alpha, that's what this is all about. It's the dot product of those vectors divided by those magnitudes. Of course, those magnitudes are easy. They are the radius of the Earth. Both of them are the same. So let's do the dot product first. Remember, with the dot product, you would multiply this component times this component, and then add all these together. That's 3,849,469.92 plus, and then the next one, multiply these guys together. One's a plus, one's a minus, so this is negative. And finally, the last two, they get multiplied together. 2299.58 times 2208.67. I get a little over 5 million. This one's a little over 6 million. Combining all that together. Now this is just for the dot product, so let's put all this together. Alpha is actually cosine inverse. And by the way, that alpha is always between 0 and 180 from the cosine inverse, which is perfect. All you need is an angle between 0 and 180. We don't need to if we're looking for the shortest distance, it'll always be less than 180 degrees. The worst case would be going all the way around the world exactly 180 degrees. So what I'm doing is this vector dot this vector divided by these magnitudes. We just did the dot product. Each of these magnitudes is the same. It's 3960. I'm going to type this into the calculator and you get cosine inverse of something around 0.18. I want to be pretty accurate here because, we could try to get something, we don't want to be off by hundreds of miles, so let's be really accurate on this calculation. And then taking a cosine inverse 79.298 degrees, because I was in degree mode, but I can't use degrees in that last step, so I need to convert that to radians. That's about 1.384 radians. All right, and that's the value that I can use. So yeah, there's the calculation one more time. 79.28 degrees, converting to radians, 1.384 radians. So my distance, S or D, I guess I had called it D in this video, that's D, is rho times alpha. Rho is the radius. The angle, 1.384, gives me 5,480 miles distance. Now, we can get little changes of several miles just depending on how accurate or what value we might choose for rho and how accurate we measure this angle. That could have a pretty big effect on our answer. But we're going to estimate about 5,480 miles. That is the straight line as the crow flies, assuming a spherical Earth and assuming a radius of 3,960 miles everywhere. 5,480 is that distance. Let's take a look at what that looks like. This is the path if you look on a standard Mercator map. It's a really distorted path there that doesn't look at all like the shortest distance. But if you look at another perspective, you can see how that slanted line, or that very curved line there in the Mercator map, is really a straight line on the surface of the Earth. It's a portion of a great circle. These great circles are these circles that encompass the Earth that have their center of a circle of the great circle as the same as the center of the Earth. These great circles are also called geodesics. So this is a portion of the geodesic that contains those two cities of LA and Tokyo, and that distance is my 8,000, what did I come up with? 5,480 miles. 5,480 miles from LA to Tokyo. So I'm looking at here a website, gcmap.com, Great Circle Mapper, that can show me that path from LA to Tokyo, and I can check to see what it comes up with as a distance. And I feel like pretty good. I got pretty similar answer as to what this website has, so I feel pretty confident with my answer. Another place I could check my answer is on Wolfram Alpha. And actually that comes up 5,480 miles. That's actually exactly the same number that I got. Tells me about how long it would take flying at 550 miles per hour. That's where this image comes from. One other place to do this calculation to visualize it is here in Mathematica, and I've got LA here at 33.9 north and 118.4 west, and Tokyo at 35.5 north and 139.8 east. In this app, I need to measure distances in kilometers. So here's the radius of the Earth in kilometers, and there's the great circle distance, the geodesic, the shortest distance between those 2 points. It's a straight line on the surface of the Earth. It tells me the distance at 8820 88.3, but that's in kilometers. Yep, and converting that 8820.3 kilometers into miles, I get that 5,480 roughly that I was expecting. Okay, so that's the end of the video. I hope it was interesting and helpful.